So today we're going to be deriving kinematic equations. I really like this part of physics because it actually allows us to see behind the curtain a little bit. A lot of times science seems like a magic, and this allows us to kind of see where some of these formulas come from. If you're really interested in physics, this is going to be especially helpful if you go into AP physics and then on. We really don't touch on where these equations come from much, but in this section we actually get a chance to see how we get to these basic equations. Which again, if you're interested in going into physics, is kind of fun because you get to see it is not a magic per se. So before we begin, I do want to make a caveat. So we're going to make the assumption that all problems have a constant acceleration. That's going to make some of this a little bit easier. If you get into calculus and beyond, you can do a lot more with these formulas. But for what we're doing here with, really we're just going to touch on basic algebra. So I don't want to get too far into it, so that's why we're going to have this caveat. So now if you recall, we have our velocity and time graph. And so if we have a velocity here, I'm going to try and keep my colors right. If we have a velocity and time, our slope here is going to be our acceleration. Because if you remember, acceleration is equal to delta V over delta T. And if you watch my previous video, I try and keep acceleration as orange, velocity as blue, and time as this pink. That being said, this is going to have a lot of steps, so when I'm starting a problem and ending a problem, I'll try and keep them those colors, but in between I might be using whatever color, either green or yellow probably, as the steps progress. So we know that our acceleration equals delta V over delta T. And what that means is our delta V is our change in velocity. So that means we have our velocity final, or our current velocity, minus our velocity initial. And the same is true for the bottom. It's our time final, or our current time. And then we're going to minus our, our time initial. So that being said, we usually, for these problems, will start with our time initial being 0. So if that is 0, we can actually cancel it out. And if instead of saying final, we're talking about current, we can leave it as just V, and that is still going to be minus our initial velocity. And instead of time final, we're just talking about our current time. We can leave it as T. So it's important to note that we're only talking about this when our T is equal to 0, our T initial is equal to 0. So our most of the cases here, we're going to have T initial is equal to 0, which allows us to cancel it out from our formula. need to get my colors back. So if we wanted to isolate our v here by itself, this one here, using this full equation, it would end up being, v is equal to acceleration times time plus our velocity initial. So, and this is some pretty old algebra, So we just moved the t over here by multiplying both sides, and then we added velocity initial to both sides. So those were able to move over, and that's how we get this formula. And we're going to call this equation 1. So now, and remember to keep this in your notes. This is something important, especially if you're in my class for physics. We'll be using this a lot throughout the year. So now again, recall. If we have our velocity time graph, and we have our line start from here, this part here is our v initial. And if we rewrite that like our y equals mx plus b formula for linear equations, our y-axis here is going to be v, and our slope is our acceleration, which is this line, and that's our m. And now along our x-axis is time, and our b, like we said, is our velocity initial, so vi. So that should look familiar because we just derived where that came from back up here. So now that we have that, I do want to remind you that if instead of a VT graph, we have a position time graph, and our slope, remember our slope is velocity, so I'm going to say it's also, that's our average velocity. That's what this line here means. We're talking about our average velocity. And when we're talking about our average velocity, this is going to be our change in position over our change in time. This should all be reviewed so far. We talked about this formula the second week of class, I believe, and this was just this last week, this one up here. So now, if we have our average velocity is equal to delta x, or change in position, over change in time, or our time initial, our time initial is 0, so it ends up becoming equal to x final minus x initial over t. So, and also if we're talking about our average velocity, thing to remember, our average velocity is going to be our velocity final plus our velocity initial. And we're going to divide that by 2. That's how you take the average of two numbers. So, and like we said before, this will become v instead of v final. That's our v for wherever we're at now, our velocity for wherever we're at now. And our v initial will stay the same, and we'll divide by 2. So now if I have v plus v initial divided by 2, that's going to be equal to our average velocity. What's also equal to our average velocity is delta x, delta x over delta t, or just time. So I'm going to actually erase, because again we're assuming we start at 0 seconds. So if we take this and we isolate our delta x by itself, if we multiply both sides by delta, or just t, sorry, excuse me, we multiply both sides by t, we have our velocity plus v initial divided by 2. And we multiplied both sides by t, so now we have a t out here. So, and this is actually going to be our equation 2. So now if we take equation 1, we'll go back up here and grab it. So if I take this equation, and let's move it down here. So these were stray marks. So this is our formula. So now if we wanted to substitute equation 1 into equation 2, we would put it up here. So again, our delta x is going to be equal to, now we're going to place this formula in for v here. So we have acceleration times time plus vi, put parentheses around that. And now we're back into this equation. We have plus vi again. And close that big bracket, and it's still divided by 2. And we still have a t out here. So I'm going to stay in green while I derive this down, just because it'll be faster for us. So delta x is equal to, and I'm going to pull this 2 out in front, so we now have 1/2. And that is going to give us I'm going to stay in green, at plus 2 vi, or v initials. I'm going to close this bracket, and again this 2 has been moved out here. and we have our time out here. So now we have to distribute the time. So we'll multiply it here. So, and again, I'm going to leave this half out in front. A times t, which would be t squared, plus 2 velocity initials times time. So now we have our delta x is equal to, and I'm actually going to distribute out this one more time, but this will give us our final formula, so I'm actually going to put it in the correct colors this time. It's going to be our delta x is equal to, and I'm distributing this out, so we still have 1/2 acceleration times t squared plus, and so we're distributing this out to both of them, and 1/2 times 2, those will just cancel each other out, and we are left with velocity initial times time. So now this is our change in position, or we can also call it our distance. And this here is going to be our equation number 3. So now, if you're in my class, this equation is actually already on our board. Actually, all of the equations we've done so far have already been added to our list of equations, but we're just deriving where they came from. So now we still have our first equation, which I'm going to bring down again. Let's bring in all that. Alright, I'm just going to rewrite it. So our first equation is V is equal to a t plus v initial. So now let's say this time we wanted to solve for t. So if we want to get t by itself, I'm going to make a line here, because remember, everything we do to one side we have to do to the other. So I'm going to subtract vi from both sides. So that cancels out that. And this gives us v minus vi. And that'll give us at on the other side. And again, we're trying to get t by itself, so we have to divide both sides by a. Divide by a, which will then give us v minus vi over a is t. So now we can substitute this into this equation for our t values. So now we have delta x is equal to 1/2 a. Now instead of t, we're going to plug this in. So it's going to be v minus vi over a. Now don't forget that this t here is squared. And we have v initial. And now instead of time, again, we're still plugging this in. So it's going to be times v minus vi over a, and these should be green. So now we've replaced all of our t's with our v minus vi over a, or velocity minus velocity initial, divided by acceleration. And so I'm not going to go through all of the steps here, but I will tell you that this will simplify. And if you want to do it, I absolutely recommend it, just so you can see for yourself how this simplifies. But this will actually simplify down to delta x is equal to v squared minus our v initial squared all over 2a. So just to make this a little clearer, I'm going to erase this for just a second and just rewrite it. This is delta x, and it's going to equal this whole thing. So now if we wanted to get our velocity, so our current velocity, again by itself, it's going to be v squared is equal to v initial squared plus 2a delta x. So now this is actually our equation number 4. So, like I said, if you don't believe that this comes through, I highly recommend trying to move your units over yourself and get to this v squared by itself. So this is called our time-independent equation. And so, if you can't tell by the name, the reason we call it the time-independent equation is because we do not need to know the time to find any of these variables inside. So this can be really helpful when you know a distance and an acceleration, and then you have an initial velocity, which sometimes is 0, especially if they tell us an object starts at rest. So now these are the 4 equations that are going to be very, very important in our class. So I'm going to rewrite them all just so they're all in one place for you. So, and you do have them in your notes because of course you were following along with notes the whole time. So I'm going to say the first one was our current velocity is equal to our acceleration times our time plus our velocity initial. This was number 1. Now our second equation was delta x is equal to our velocity initial plus our velocity, our current velocity, and divided by 2. And that whole thing was multiplied by t. And that was our, this was our equation number 2. And our equation number 3 was d or delta x, or change in position, is equal to our velocity initial times our time plus 1/2 a t squared. So this was our number 3 equation. And then our 4th equation was the last thing we derived, and this was our time-independent equation, which was velocity squared is equal to velocity initial squared plus 2 a, and then our change in times our change in distance. So, and to undo this square, if you need to, it's going to be a square root over this whole thing. But this was our equation number 4, and again, this was our time-independent one. But these are the 4 major equations we're going to be using for motion. I highly, highly recommend you get acquainted with them and figure out how we got from one to the other. Please rewatch this video as many times as you need, like you needed permission to do that. But otherwise, if you're in my class, please ask questions. But otherwise, you have a worksheet in our class. I will try and put it in the comments below. I had problems with that with the last video, but hopefully this one will work a little bit better. Thank you, and I hope you enjoyed this video as much as I enjoyed making it.